All right, since we had some technical issues associated with the whiteboard software in class today, I decided to post this short little video summarizing the calculations for the example that we did in class. So here's the summary of the example. The idea was to take this and evaluate ACI requirements for the beam. So I have here all of the calculations performed in one sort of neat set of notes, so you all can pause the video if you need to jot any of this down. I'm going to go through the calculations somewhat expeditiously to make the video somewhat short. So here's our beam. The width is 10 inches and the depth, or the effective depth, is 23 inches. We have 3 number 8 bars with an area of steel of 2.36 square inches. Now, a couple of things over here on the left, we know that we have 4 KSI concrete, and after lecture today and just looking at beta 1, we realized that for 4 KSI concrete, or for any concrete that has a compressive strength less than or equal to 4 KSI, the beta 1 value is 0.85. Remember, beta 1 relates the depth of the stress block to the depth to the neutral axis. Now, our steel is grade 60, so it's 60 KSI yield strength. And we'll need that to do strain comparisons later on. Now, speaking of, here is our strain profile. Remember, from the top to the neutral axis, we turn that C. This is D minus C. Our maximum usable strain in the concrete we define as 0.003. So what we really need to find is epsilon sub T. This is the strain in the tensile region. Remember, we assume a linear strain profile, and regardless of your compressive strength, we assume the same maximum usable compressive strain. So this is really just similar triangles. You know, 0.003 is to whatever this depth is, and that's got to equal epsilon sub T is to whatever this depth is. So we need to look at some strains. So over here on the bottom, I'm calculating some strains. I'm starting off, I'm taking A over beta 1 to calculate C, because A equals beta 1C. So if you recall, this is from our last example. Our A value was 4.165 inches. I also went ahead and threw the nominal moment capacity. That's what we did in 5A, the example 5A. We ended up getting 246.8 foot kips there. So C comes out to be 4.9 inches. So when you calculate the strain in the steel, it comes out to be 0.0111. Now, comparing that against the strain at yield, which is just Fy over E sub S, so Fy is 60 KSI, the modulus of elasticity of steel is always 29,000 KSI, comes out to about 0.002. So right off the bat, we can make really 3 key observations. The first one, if you recall in example 5A, in order to compute the tensile force that is in the steel, we made an assumption that the steel had yielded. That is a very valid observation to make, because if you compare these two, you will see that epsilon sub y is way smaller than this. This is about 5 times bigger than epsilon sub y. So the strain in the steel is far higher than the strain that would be required to cause yielding, so that's a very valid assumption. Also, looking at this number, we can make 2 other really important observations. If you recall, there's an ACI requirement that the strain must be greater than or equal to 0.004. That has been met. There's also an observation that can be made because this strain value is larger than 0.005. The strain in the steel is basically the key factor in determining what your strength reduction factor is, your phi value. But since this strain is much larger than 0.005, we determine that that is tension controlled, and our phi value is 0.9. So if we have our phi value and we have our nominal moment, the phi mn calculation is quite simple. That's pretty straightforward. So phi mn comes out to be about 222 foot kips. So that is the maximum usable flexural capacity of this section. In other words, you apply load over that, you have essentially failed the concrete beam. Although, to be clear, the beam can probably withstand a little bit more moment than that, but we say that's the maximum usable capacity because we've applied all of our appropriate uncertainty factors. That's what phi is. Phi is accounting for that uncertainty. So this is what I can sort of hang my hat on, if you will, in terms of capacity. Okay, The last thing, and this is what I had mentioned at the end of class, is something you could do on your own. This is a very brief set of calculations. So the minimum steel requirement, B sub W, which is the width of the web. For a rectangular beam, it's just the width of the beam, so that's 10 inches. The effective depth is 23 inches. That's just from the previous panel. And you can see here this equation that I am boxing. That is the minimum area of steel. That's how you compute what is the minimum amount of steel that you must put in a reinforced concrete beam. So what I've done over here on the side is I went ahead and computed 3 square root of FC prime. Now 3 square root of FC prime, when you chug that out, comes out to be about 190 psi. Now if you look inside the, if you look at the expression, you're taking that fraction and you're multiplying it by the maximum of either 3 square root of FC prime or 200. When you do the math, you find that 200 is larger. So if you can see here on the bottom, I'm just taking BWD over FY times 200. So that's why I have that here. So plug and chug, and you get a minimum area of steel of about 0.77 square inches. So that would be the absolute minimum amount of steel we can put in this section. But if you look, I mean, we've put much more than that. The actual area of steel was about 2.36. So we've definitely met the minimum requirement, minimum steel requirement for this section. All right, that concludes the example, and next we will look at beam design.